So we're going to take a look at the notes for 6.1, and we're only going to get a chance to do kind of the first couple of pages of that, like first 6 pages or so. But it's the important stuff where we're introducing kind of what's going on with this new concept. Let me click over to that. The new concept of the Laplace transform. So up to this point in your life, you have run into all kinds of really cool operators. When you were a little kid, somebody taught you about the addition operator, and you probably don't remember. Most people don't remember when they were learning to add, as little kids, and somebody's like, if I have 2 and I have another one, it becomes 3. And that's the magic of the addition operator. And you're like, oh, this is so cool. Most of us don't remember that. You might remember operators like division, especially like long division. You remember the algorithm for long division when you learned it as a little kid? No, maybe not. Or did they just hand you calculators and say, do it on the calculator? Yeah, probably pretty much. Okay. Well, most people learn different operators at different times or kind of consistent times. And it's usually right about the time you get into operators like the exponentiation operator, the natural log operator. And you're like, okay, so this is just a new kind of function. And then you get into calculus and you learn about the limit operator. And then the differentiation operator, what we call the derivative. And these all have their own particular language, their own grammar. They behave in particular ways. And so usually it's limits and derivatives. That's the first time that people are like, whoa, okay, this is new. This is very different. And then, of course, the integral operator. And it's probably been a while since you've run into a new operator, but we have a new one here with us today. Specifically, we have the Laplace transform. And so the transform, the Laplace transform, literally turns some function into a different function. That's it. That's what it does. The Laplace transform takes some function, little f of t, and so yeah, it's a function of time. That's the input. And the output is some function of a new variable, s. Notice capital F should look kind of familiar like the old days of Calc 1 when you learned about integrals and capital F and lowercase f and stuff like that. It's similar in terms of how it behaves. But for our purposes, you need to think of the Laplace transform as kind of a machine that comes along and goes, grabs onto a function of t and poops out a function of f or a function of s. That's what it does. Except there's no smell. It's not at all disgusting, and it's completely sanitary. It's a nice thing about mathematical functions. They're completely sanitary. So it does this by comparing. This is really kind of behind the scenes what it's doing. It's comparing the function f of t with some standard function e to the st. So it's basically asking the question, how much is this function f of t like the standard e to the st function? Right. And you'll notice up here there's a new operator symbol. Instead of calling things, capital D for derivatives, we're going to call it capital L for the Laplace. And the other way that this sometimes shows up is the script L. Right. This L will appear in books. It'll appear online and things like that. But sometimes it's just capital L that's bold-faced too. Depends. So when we say it's comparing things, it's essentially asking the question and answering the question, how much is the given function like some particular standard function? So it's saying things like, how much is a water wave like a sine curve? That's the kind of thing that a Laplace transform could answer. And you're thinking, okay, what kind of answer does it give? And here's the funny part. The answer that it gives is a numerical value. That's it. So it's a way of quantifying this similarity, right? Not just saying, oh, it's kind of like it, it's sort of like it. It's actually a numerical value that we can compare and say, oh, this one's more similar than that one, right? It's quantification. So we can also do things like a sound wave. How much is that like a cosine curve? right? Or we could be closer to home and say how much is an oscillator's position, like an exponential decay. Right? So notice it's not all about waves. It could be about anything. We can ask this question. So the reason that you'd want to do this and do this Laplace transform is because it allows us to say, hey, this is similar enough to this other kind of function where we can kind of translate into Laplace land, solve a problem in Laplace land, and then convert back at the end, and it's made our entire problem solving process much easier. So it's kind of like, it's like translating from math to English, solving in English, then translating back. And so that's what we're going to be doing with the Laplace transform. We're going to be using it to take a really complicated problem, and sometimes complicated problems that there's really no other good way to solve analytically. We're going to convert from a Laplace transform, or excuse me, using our Laplace transform, we're going to convert this nasty looking problem into something that's simpler, that's easier for us to manipulate and solve in Laplace land. And then we're going to solve it in Laplace land and then convert back into our world, and we'll be able to say, hey, there's the solution, and in a way that we wouldn't be able to do just manipulating using the strategy. So it's basically just one more strategy that we have for solving problems, right? So down at the bottom, you'll notice it turns out that Laplace was probably, almost certainly, as a matter of fact, certainly not the first person to discover this. Pierre-Simon Laplace was a mathematician, an engineer, a really smart guy, but he came about 100 years later than Euler. And we're pretty sure Euler came up with it first, this idea first. But unfortunately, if we named everything after Euler, there'd be very few things that didn't have Euler's name attached to them. So it became the standard practice to just name things after the next person after Euler to discover them. I mean, the lower hanging fruit. So we call it the Laplace transform. Or later on, another one that you may be familiar with, I don't know, the Fourier transform. It looks like Fourier, but it's Fourier transform. That's another one that does a similar job to what the Laplace transform does. And that's another example of, we're pretty sure Euler got there first, but we named it after Fourier because, you know, it's just a cool name. So at the top of the next page, we're going to formally define what this Laplace transform looks like. How is it defined? And so what we want to be able to do is we want to transform the function y into the function capital Y. So that's the transform. So we can take the Laplace transform of this thing right here. That's the object of our transform, right? That's the input, if you want to think of it this way. And this over here, that's the output. And bonus points if you're paying attention and you realize, hey, that involves an integral. You're right, it does. Not only does it involve an integral, but notice what kind of integral it involves. Somewhere your Calc 2 instructor is bouncing up and down in their seat with glee, waiting for you to recognize what kind of integral that is.
Open-ended?
Yeah, a fancy name for it is anybody know what the fancy name for it? Open-ended, I like that because it goes to infinity.
Is it indefinite?
Close, it's improper.
Improper.
It's like, oh heavens, it's the kind of integral that insults your mother, right? No, this is an improper integral because we can't actually plug in values of 0 and infinity. because infinity is not a number. You can't just substitute it in. So we have a technique for solving this that you learned in Calc 2. Oh, you learned it. Whether you remember it or not, we'll see here in a minute. But this thing is an improper integral that takes off and goes from 0 to infinity. Notice it always starts at 0. It never considers negative values of t. So notice this is always about t being greater than or equal to 0. So that's important. We only care about positive time, right? Starting at t equals 0 and going forward. So Laplace transform, anything having to do with the Laplace transform, it's wherever you mark your 0 time, everything from there onward, or onward, depending on which direction. I can't tell. Which direction is correct on the video? Is it this way or this way? That way, that way? Does it look right when I do it this way? Positive is that direction? Is that looking correct? I think it's looking correct. I don't know. So notice, this thing is the mechanism. This is the operator that we're going to apply to our input function, little y of t. And it's for all numbers s for which this improper integral converges. And if you remember, converges means has a definite value. And so that's where we have our Calc 2. Whoops. Calc 2 flashback right there. Hopefully it's a good flashback. If it's not a good flashback, then I apologize. I don't know what to tell you. Most Calc 2 flashbacks are not very good in my experience. Most people just go, oh God, yeah, I remember that. I'll never be the same, right? That's okay. So what does that mean? Well, that means we only care about where the integral converges. And those specific x or s values. All the other ones, any other s value that might exist, we don't care about those. We only care about the s values, the output s values, where that integral converges. So keep that in mind. Sometimes the Laplace transform gets written like this, capital Y, big capital Y. Notice not a vector. This is not a matrix Y. This is just capital Y, not capital boldface Y. Can be written as the script L of little y. Notice the input in there, operator, output, or sometimes just with a capital L. Either way, this is just the shorthand notation for function of input is the output, right? So if you were reading this, you would say, capital Y is the Laplace transform of little y. And you have to use that accent too. I don't know why it works that way, but you just have to. So Stephen, I'm expecting that nice microphone to really help out with that. Okay. So let's take this for a spin and see what we get. So up here, that's the definition of the Laplace transform. So let's go and see what we get. What we're going to do is we're going to take the Laplace transform of e to the 2t. So this right inside there, that's my little y. Little y of t equals e to the 2t. And so this whole thing has to be, by definition, equal to the integral from 0 to infinity of y of t, so e to the 2t, times e to the negative st times dt. Okay. Now we're going to manipulate this. Before we do our Calc 2 flashback, we're going to manipulate this. And you'll notice it's kind of nice because we have the same base and we're multiplying two things that have the same base. So that means that we can just combine their exponents. So we're going from 0 to infinity of e to the 2t minus st dt. And as you can probably see, we can factor out a t up in there. e to the t times 2 minus s dt. Now, if you're sitting there thinking, okay, wait a minute, what's s again? Remember, s could be any number. We're interested in what values of s make this thing converge. And what makes this thing converge is where is this integral equal to a specific definite value, not where does it blow up and diverge. So what I really want to do is have our little Calc 2 flashback in the next line. And the Calc 2 flashback, if you remember, is we're not going to integrate this thing from 0 to infinity, but what we're going to do is we're going to integrate it from 0 to, say, b. And then out front, we're going to take the limit as b approaches infinity. So we're being a little sneaky, but we're saying let that go from 0 to b of e to the t times 2 minus s dt. Now notice, by doing this, I've sort of put off until later that b approaches infinity business. Inside is an integral that I can totally evaluate. And then once I've evaluated this integral, then I can evaluate the limit to figure out which values of s make it converge. So my next step, how are we doing up to this point? We all okay with that? Is that our Calc 2 flashback? Everybody okay? Need to get a drink? Maybe? Wrap yourself in a warm blanket, depending on how Calc 2 went for you. Bryce, you got the shakes, I can tell. You got that look. Calc 2, man. I don't like to talk about it. Okay. So what we're going to do now is evaluate inside the parentheses. Don't worry about the limit right now. Hang on to that for later. Inside here, we have e to the power some junk, blah, blah, blah. There's this thing right here, the 2 minus s. That's just a number. We don't know what s is, but s is definitely a number, right? So it's not a variable. It's not dependent upon t. So we're just going to treat it like it's a number. So this thing, if you integrate it, becomes, with a little bit of help from a u substitution, becomes 1 over 2 minus s out front times e to the t times, 2 minus s, still on the inside there. And this thing is going to be evaluated from 0 to b. Right? And again, the question is, where does this thing converge? Well, if we evaluate it when t equals 0, this becomes 1 over 2 minus s times e to the 0. E to the 0 is just 1. If I evaluate it when t is equal to b, then I get something a little different. So continuing on my process here, limit as b approaches infinity of, inside here we're going to have, I'm going to factor out the 1 over 2 minus s because that's going to be the same thing for both of my terms inside there. And so we'll have e to the 2 minus s times b minus e to the 0 times 2 minus s, or just e to the 0. And because we know e to the 0 is just 1, it doesn't go away, it just becomes a 1. We can say this is still, haven't evaluated the limit yet, still holding off on that, limit as b approaches infinity of, this is 1 over 2 minus s times e to the 2 minus s, in parentheses, times b. Now what happens if I let b go to infinity? What do you think? Well, there's no b out front, so that doesn't matter. The b upstairs here, what happens if b gets really, really big? What happens to e to the 2 minus s times b?
It'll just go to infinity.
It will go to infinity if s is smaller than 2. You see it? If s is smaller than 2, that exponent, or this exponential, will just take off and blow up to infinity. But what happens if s is less than 2? Nothing?
Will it go to 0?
Yeah, so take a look at this. If we've got two situations here to pay attention to. I don't know if this green marker is going to work. If s is greater than 2, then we have the limit converging. Because if s is greater than 2, this thing, 2 minus something bigger than 2, is going to be a negative value. A negative number sitting in front of the b. As b gets really, really big, this is e to a negative power. That goes, heads towards 0. This thing converges. But if s is anything that is less than 2, let me use a different color for that one. Let's see this one. If s is less than or equal to 2, the limit diverges. And diverges is bad. That's what we don't want. We don't care about diverges. We only care about where the thing converges. It's a little fancy footwork there, but is everybody clear with this situation? The correct answer to what happens as e or as b approaches infinity is, well, it depends on what s is equal to. Because if s is a big number, bigger than 2, then the limit converges. If s is smaller than 2, or equal to 2 for that matter, then it diverges. And by the way, it diverges when s is equal to 2, because the thing sitting out in front is going to wind up causing problems.
I just have a quick question.
Sure, yeah.
When the e to the 0 goes to 1, it would be minus 1 there, and do we just not care about that to carry into the next line after that?
Oh, you're right. I'm sorry.
I was just
forgot.
wondering.
I closed my parentheses off too quickly. I was more concerned with that first term, but there is a minus 1 sitting over there. So if I multiplied it through, yep, thank you, good call. That would be minus 1 over 2 minus s. Yes, sorry about that. I was concerned with the first term, but the second term is still there. That's important, right? And so if this thing converges, which is what we're interested in, then this whole first term just fades away to 0, because e to the negative power, as that power gets bigger and bigger and bigger, bigger negative, that whole thing just fades away to 0. So I'm going to continue this up here and say, I can't fit it all on the screen. They're close. So provided s is greater than 2, then capital Y of s, the Laplace transform of this f of t right here, the Laplace transform is going to be equal to just plain old negative 1 over 2 minus s. Because that first term, let me scoot it down so you can see, that first term disappears when it converges. And all you're left with is negative 1 over 2 minus s, which, by the way, you can rewrite, and this is the way we're going to do it. We're going to say that thing is equal to 1 over s minus 2. It's the same thing. We've just kind of pulled the negative into the denominator, right? And so that means, since I have a spaz out dog who's decided to nest on their bed behind me. So that means the Laplace transform of e to the 2t is equal to 1 over s minus 2, provided that s is always greater than 2. So all we did was we followed the directions, we followed the definition of the Laplace transform, we applied the Laplace transform to this function right here, y equals e to the 2t. And we said, what do we get? Where does that integral converge? And it turns out it converges only when s is greater than 2. And when it converges, you wind up with some function of s, specifically 1 over s minus 2. Do you remember the first time somebody showed you the derivative operator? And you looked at it and you're like, what the hell does that mean? That's the next question that should be going through your head right now, which is, okay, I just did some calculus. I had a flashback to Calc 2. You made me relive Calc 2. How dare you? And what do we have to show for it? We have now a new function of 1 over s minus 2, provided s is greater than 2. What does that tell us? Well, I'm so glad you asked, because that's what's on the next page. So a couple of things to ponder about the Laplace transform. Strictly speaking, the value of the Laplace transform at a particular s value measures the similarity that that function, that y of t, has with e to the st. So whatever s value you pick, it'll say, remember that original y of t function that you started with? This is how similar your Laplace transform is to that. So, since we know that the Laplace transform of y of t, this thing right here, is really just a, oops, not a g, quantification of similarity. Between y of t and e to the st. That's all that it does. It gives you a number. It spits out a number when you plug in an s value. So let's see how that works. Since we know for y of t equals e to the 2t, that was the function that we just found the Laplace transform, we know that the Laplace transform of e to the 2t is this thing, 1 over s minus 2, for any s value greater than 2. We know that's true. We just proved it. So what does that mean if s equals 3? Well, if s equals 3, then you'd plug in 3 over here, and you'd say y of t equals e to the 2t, and e to the 3t, that's the e to the st, right? Or e to the 2t and e to the 3t are similar because L of y of t when s equals 3 is 1 over 3 minus 2 equals 1. That is the Laplace value for s equals 1. So they have a similarity of 1. These two functions right here have a similarity of 1. You're like, whoop-de-doo. Well, what if s equals 4? That means we're comparing e to the 2t, our original function, and e to the 4t. So what does it mean to compare those two things? Well, if s equals 4, then they have a similarity of 1/2. You're like, okay, so it's just a number. Yes, but notice, are we more similar or less similar than the previous example?
Less.
Yeah. Are you surprised that e to the 3t is more similar to e to the 2t than e to the 4t? You're like, well, I mean, they're both exponentials, but e to the 4t is a bigger exponential. So of course it's going to be less similar to e to the 2t.
Do we not care about negatives then when we're comparing this?
Well, how would you be able to get a negative?
Like if we do e to the negative 2t, would that be 1 over negative 4?
Well, remember, this is the function that we're comparing, and the standard function is this guy. So the only way we'd be able to get a negative is if we plugged in an s value over here that was less than 2. But we've already said you can't do that.
Oh, that's fair.
That makes sense?
Yeah.
So let's do one more just to make sure that we get the hang of this. What happens if s is 2.1? Just for giggles. 2.1, that's pretty close to 2. Remember, we're comparing to e to the 2t. So we're basically comparing the two functions, e to the 2t and e to the 2.1t. What do you think? Are they going to be more similar or less similar than the two previous examples that we've seen? What's your gut tell
Less?
you? What's your gut tell you? Are these two more similar than those two?
My gut tells me not to trust my instincts.
My gut says don't trust my gut. Well, let's find out then. If you got a guess, stick it in your head for right now. I'm going to throw this value of s into my formula. 1 over 2.1 minus 2. That's the same thing as 1 over 0.1, or 1 over 1/10, which is equal to 10. So if you were comparing, you would say, wow, that one has a very large Laplace number, which means that it is, by comparison to the other two functions, e to the 2.1t is much similar, much closer to e to the 2t than e to the 4t is, or than e to the 3t is. So all we're seeing is that as the s value gets further and further away from 2, the Laplace transform gets bigger and bigger and bigger. So I'm going to kind of summarize that down here. As s approaches 2 from the positive side, the Laplace transform, I should say the Laplace value, Laplace transform value gets huge. So as we get closer and closer to 2 from the positive side, the Laplace transform value blows up. It gets huge. So that means more similar. And vice versa, as s approaches infinity, positive infinity, goes away from 2, the Laplace transform value gets tiny, which means less similar. The Laplace transform allows us to have a quantitative comparison of multiple functions. Right? E to the something t. Okay, which one of those curves with what value of something is going to have us the most similar to e to the 2t? When I put it that way, you're like, well, duh, obviously 2, right? That's the most similar. But notice, s has to be greater than 2. So as close as you can get to 2 on the slightly larger side, that's going to produce the most similar results. And by the way, we can use this to our advantage, use the same technique to our advantage to solve it generically for any old exponential. So let's say we want to take the Laplace transform of something like this, e to the a t, where a is any number. Well, that's just the integral from 0 to infinity, right? That improper integral. Oh, heavens, it's improper. Times e to the at times e to the minus st dt. So that's using our definition of the Laplace transform. So what we're basically saying is, I've got a function e to the at. How similar is it to the function e to the st? Well, let's find out. So no big surprise, this is going to wind up being very similar in structure to what we just found for the particular case of e to the 2t. So for this one, we've got an integral from 0 to infinity. This is going to be e to the a minus s times t dt. And you can probably see we're just going to use that same Calc 2 flashback and write it as a limit as b approaches infinity of 0 to b of e to the a minus s times t dt. And very similar to what we did last time. The only difference is we don't know what a is. A is just a placeholder, could be any value. So this thing becomes limit as b approaches infinity of, now what's inside here is this thing evaluated. So that's going to be 1 over a minus s times e to the, well, this is going to be a minus s times b minus 1. Should look very, very similar to what we did last time. Instead of a, last time we had it as 2. And so this thing only converges, and that's what we care about. We don't care about diverging. We only care about where it converges. This converges if and only if s is greater than a. So values where s is less than a or equal to a, completely can't consider those. So in general, there we go, for our exponential curve, e to the at, the Laplace transform for e to the at is exactly equal to 1 over s minus a, as long as s is greater than a. So we just did this in general for an exponential. But I know what you're thinking. You're thinking, Steve, the world is not just exponential functions. What about our old pal, the polynomial? What about our dear friend, the sine curve or the cosine curve? What about those? Have you forgotten about those? No, I have not. But you would find it using the exact same method. Instead of plugging in e to the at here, you'd plug in sine of t times e to the minus st times dt. And you'd evaluate that integral. Do you see how the Calc 2 flashbacks start to come, as Vin Diesel would say, more fast and more furiouser? You see the problem? The function that you plug in here, this is the thing that you're taking the Laplace transform of. The thing that you plug into that formula only serves to make your integral more complicated. But fear not, because on the next page, I have for you a lovely little table of handy Laplace transforms. You want to know what the Laplace transform of e to the at is? No worries. It's 1 over s minus a as long as s is greater than a. You want to know what the Laplace transform of sine of omega t is? No problem. It's this. Omega over s squared plus omega squared. You're like, oh, God. But omega, remember, is whatever is inside the argument of that sine function. And I wonder why we're using the letter omega there. Does it look familiar? It should. Because, of course, that's frequency, right? Angular frequency, but it's frequency. And so this is going to play right into our hand later on when we're going to use Laplace transforms to be able to solve some problems. So notice, we can not only take the Laplace transform of an exponential, we can take the Laplace transform of a sine curve, we can take the Laplace transform of an exponential times a sine curve. Hot diggity, how about them apples? We can go get a box fan to make things a little bit cooler in our room even. Right, Bryce? I saw him walk by with a box fan in his hand. That's pretty funny. Hopefully he's okay. Is that your biggest fan? And so those are the answers for the final exam. I'm really glad you guys were paying attention over the last. Oh, hey, Bryce, how's it going? I'm kidding. I'm kidding. We saw you walk by with a box fan. I thought it was pretty funny. So is it to keep cool?
Yeah, I'm starting to sweat.
Laplace transforms can do that to you. They really can. I know. So notice, not only do we have Laplace transforms for exponentials and sine curves, we have combos, a multiplication of an exponential and a sine curve, a linear function times a sine curve, oh, what the hell is that thing? U with a subscript A? What's that? Have you ever seen that before? This is new. This is coming in section 6.2. That'll make a whole lot more sense in section 6.2. It's something called a heaviside function. And if you think that word is made up, well, all words are made up, so get over it. But no, that is not a made up word. That's actually somebody's name. And we're going to learn all about the heaviside function in 6.2. Over here on this side, you can take the Laplace transform of t to a power. So this is the basis of our polynomial question. How do you take the Laplace transform of a polynomial? Well, right there, t to the power n. And the Laplace transform looks like this. And I don't know, I'm going to kind of scoot it over so you can see it a little bit clearer. Have you ever seen that notation, the exclamation point, before in a math class? Some of you may have run into it, others you maybe not, depending on what math you had and how complicated the teacher wanted to make things. It appears in Calc 2, depending on if you got that far. This is pronounced N. I'm kidding, it's not. It's N factorial, just making sure you're all paying attention there. It's N factorial. This notation right here, I'm just going to make sure that we're all clear with that. This thing is called the factorial notation. And if you stick it next to a number, and for our purposes, a whole number, for our purposes, a whole positive number, but if you stick it next to a number, it becomes that number times each successively smaller number. So 3 factorial is 6. What's 4 factorial? Everybody has to look up and to the right to be able to calculate that.
24.
24. What is 5 factorial?
120,
What is 6 factorial?
720.
What's 8 factorial? See, here's the problem. Factorial is one of those things that grows wicked fast. If you think exponentials grow fast, factorial's got you beat. They grow really fast. So in general, if we say n factorial right here, that means n times n minus 1 times n minus 2 times n minus 3 times forever until you get to the very end times 1. And by the way, the only other quirky one is 1 factorial is technically 1. And 0 factorial, wait for it, is 1. Oh, my wife just handed me this. This just in. This appears in Calc 2, just in case you were wondering. These appear all over the place when you're dealing with factorial, right?
Those little things mean hella bigger than.
Hella bigger than, yeah. So she's listening to me, but
I am.
I'm going to charge her a little bit of tuition, I think, in the form of supper once we're done with today. What did you bring?
I brought you goat chicken with broccoli and this big sweet.
Oh, she brought me supper. We need to wrap this up. Stevie, hungry?
Can I pay the university in supper?
Wouldn't that be nice? Sadly, I don't get paid by my institution. They just give me a handshake and a smile and a nod, and they let me just keep on teaching. Anyways, so if you've never run into factorial before, that's the one kind of weird business. We're going to get into what the Heaviside function means in a little bit, but everything else on here makes sense. The only other one that's, I should say, the only other one that's a little kooky is this guy right here. And you may actually have run into him in Maple. Sometimes he pops up in Maple. This is called the Dirac delta function. Those of you going on in any kind of mathematics, and especially if you're going on in engineering, you're going to run into the Dirac delta function, because the Dirac delta function works like this: 0, 0, 0, A, 0, 0, 0, 0. That's it. That's all that it does. I should say, when it gets to A, it jumps up to 1. That's it. That's all that it does. It's 0 everywhere except exactly at the t value of A, and it jumps up to 1, and then it's 0 everywhere else. It's incredibly boring. But it turns out it's super important for the construction of other functions. So this one right now and this one right now, we're going to pay absolutely no attention to. The others are for your convenience and for being able to make sense of that. Now, I don't want to shock you, but Maple can also find the Laplace transform of things. We're going to get to that in a second. But real quick, let's just make sure that we know how to use the Laplace transform and that lovely little table up above. And I would like for you right now to figure out what are the Laplace transforms of these 4 lovely, lovely functions. And what I'm going to do is I'm going to stop sharing, and then I'm going to put you guys into rooms. And I would like for you to, with your partners, just randomly come up with the solutions. A go. This is where we find out whether Matt actually just left the room and left his computer on. Oh, it looks like he did. Matt, you naughty, naughty. Okay, I'm going to hit pause on the recording here. After all that work. Thanks for pointing it out, though. I thought I had hit it, but apparently I had not quite gotten to the little record button. So we just went over how it is that you create Laplace transform for all of these lovely little examples that are at the bottom of the page, right? And so the ones that are on the bottom of the page, I'm actually going to do in Maple. And so let me share screen as we were doing before I realized I hadn't started sharing my screen or hit record. Poop. And so being able to type in the int trans library allows us to do Laplace transform. Laplace has 3 parts to it. Once you type in Laplace, you have to say what the function is, the right-hand side of the function, what it's a function of, what variable it's a function of, and what you'd like to turn it into, what variable. And so for us, these last two are almost always going to be t. Well, they're always going to be t and s, right? So you just get in the habit of doing that. And so we can do the other two. The next one was the Laplace transform of t squared. And Maple says, oh yeah, that's 2 over s cubed. It can use the formula that's at the top of the page 4 in the notes, but it works just as well to use Maple, right? And then the last one that we,
Laplace value.
say it again, I'm sorry.
Can we have a negative Laplace value? Like, is that ever allowed?
Negative Laplace value.
Like if we were to plug in something that gives us a negative value, like if we were to plug in something like an S that yields a negative value.
Oh, I see what you're saying. Can
that allowed?
overall, can the value of a
Yeah.
Laplace transform be negative? Absolutely it can. Absolutely it can. So for example, in that last example, if S was equal to -2, there's no restrictions on what S can be in that case, is there?
No.
Take a look at the table. Take a look at the table at the top for the polynomial.
The greater than 0 one?
S has to be greater than 0. So even for that last one, I'd love to say I could throw a -1 in for S, but I can't. It's not allowed. So as part of the integral definition of the Laplace transform, in that case right there, and again, Maple doesn't tell us that S has to be greater than 0, but that would come out when you do the actual definition of the Laplace transform. The only way the integral would converge, there we go, is if S is greater than 0. So in this case, it's not possible. For this case, it's not possible. Are there situations where you can have a unrestricted S value input that will wind up giving you negatives? Let's take a look at this last one, and then I'll explain why the answer is actually no. So e to the, what is it, x to the 2t times cosine of 3t, comma t, comma s. And so Maple says for that one, takes it a second, but it gets there. And you'll notice for this one, since we're using the e to the at times cosine of omega t, there's apparently no restrictions for what s can equal. So if I plugged in a value that's smaller than, say, smaller than 2, I'd wind up with a negative number up top. And in the bottom, I'd wind up with, well, 2 positives added together. It is possible. The problem with a negative value for a Laplace transform is it really is kind of meaningless as a negative value. The magnitude of the Laplace number is really the interesting part. For our purposes in this class, we're just going to be using Laplace as a transform as a way of turning a differential equation in one form into a differential equation in another. As you go on in other math classes and you learn a little bit more about transforms, you'll learn a little bit more about what it means to have a positive or a negative value for a transform. The short answer is it doesn't really matter for Laplace. The negatives really just come back to the that's what I'm looking for, the magnitude. Right?
So we want it as far away from 0 as possible?
So a larger Laplace value means more similarity to the curve e to the st. Right?
So really negative would be really close, right? Just like really positive would be really close?
So what I'm saying
for
is
our purposes?
really negative would be really close for our purposes, yes.
Okay.
Yes. Yep. For what we're doing right now, though, we're just learning how to make sense of the Laplace transform. So I want to share, now that we've figured out how to do this in Maple, I want to point out that there are some other things in the little explanation or the little output for with int trans where you can see there's some other stuff going on. For example, there's a Laplace transform, but there's also that. What do you think inv Laplace does? You guys are smart.
Is it the inverse?
So the inverse Laplace transform takes something that's in a form having to do with S and turns it back into something to do with T. So let me show you that this actually does work here. I'm going to start with that top one. I'm just going to be lazy and grab it here. So copy that. And I'm going to say inv Laplace, this thing, it's a function of S currently, and I would like you to turn it into a function of T. Using the inverse Laplace, my hope, fingers crossed, is that it should spit out sine of T. And sure enough, it does. So just like you learned from the very beginning in math, if you have an operator that does one thing, there's got to be an operator that goes the other direction to undo that thing. So it's that way for addition and subtraction, multiplication and division, exponentiation and logarithms, differentiation and integration, Laplace transform, and inverse Laplace transform. It's just basically another kind of direction for that operator working backwards. And by the way, you can do the same thing in Maple for all those other examples. If I start with 2 over s cubed and say inverse Laplace, then I can work back to t squared, right? And that actually brings me to the document at the top where I had written the Laplace transform is going in this direction. The Laplace transform goes in that direction. And if that's the Laplace transform, the inverse Laplace transform goes in the opposite direction. This is the inverse direction, right? So just like when you were in pre-calc and you were learning about function goes this way, inverse function goes this way, it's the same thing. It's just a different operator, right? Instead of adding turns into subtracting, we have Laplace transform turns into inverse Laplace transform, right? So at the bottom of that page, it says also check out the Laplace transform math app on Maple, but you don't have to check out the math app. You have the ability to just, with int_trans, that library, you can take the inverse Laplace or the Laplace of anything you want. Now, be warned, just because you can find the inverse Laplace or you can find the Laplace transform doesn't mean it's pretty. And you'll notice at the top of this page, there's a restricted list of examples. Notice I haven't done things more complicated than a sine curve with, just one little modification inside. Sine of 2t I can do, but sine of 2t squared, nope. T cubed times sine of 3t plus 2 on the inside there, nope. So know your limits. And we're not going to go too far into the weeds with this. This becomes a tool for us. The very last page that we're going to talk about, well, there's kind of 2 pages, but the last page that we're going to spend any appreciable time on is this inverse Laplace transform page. And, oh, sorry, no, not this one. This is the rules for Laplace transform. So this is like the grammar of Laplace. And so I want to point out a couple of these little pieces of grammar that you're going to need to pay attention to. So the first thing is you can take the Laplace transform not just of the function y, but of the function y's derivative. And when you do that, you take the Laplace transform of dy dt and you wind up with s times the Laplace transform of the original function y. Notice this is like integrating almost, plus y of 0, where this thing right here, that's an initial condition. So if you want to take the Laplace transform of a derivative, then you have to know an initial condition or have something stand in place for its initial condition, y of 0. So the good news is we can take the Laplace transform of derivatives. The bad news is we have to have an initial condition for them to make any real, actual sense. These guys, the next 2 are kind of important, and they make perfect sense when you think about them as kind of the rules that look a lot like the rules for integrals and derivatives. The Laplace transform of 2 things added together is the sum of their Laplace transforms. This is what we call the sum and difference rule. Right? It works just the same if it's two things subtracted from each other, right? So if you have the Laplace transform of two terms, that means that you can break it up and chew on each one of the terms by itself. So that's handy. It's like the derivative, it's like the limit, right? The limit operator, the derivative operator, they work that way. And so does the integral operator. If you have multiple terms, you can split them up and focus on each term. This one right here, this is the constant multiple rule. This says if you have a constant times y and you're doing the Laplace transform, you can just pull the constant out front. And so the Laplace transform of a constant times y is just that constant times the Laplace transform of y. This is the constant multiple rule. And then these last two, we're actually going to get into in section 6.2. So for right now, just hold off because that's dealing with that Heaviside function. But these last two are not terribly important for us right at the moment. They will be in section 6.2. But you'll notice the constant multiple rule and the sum and difference rule, that's going to allow us to do some algebra with Laplace transforms. We're going to be able to manipulate Laplace transforms. And so in the notes underneath here, it says we can take the Laplace transforms of derivatives, and it looks suspiciously familiar to that old pal that we had, the fundamental theorem of calculus. And if you remember, that was the integral from a to b of some function f of t dt is equal to capital F of b minus capital F of a. Where that capital F, that's the antiderivative. So this fundamental theorem of calculus is at play in our ability to take the Laplace of a derivative. Right? It's no big surprise because the Laplace involves integration. So of course calculus is involved. What's different and what's important about the Laplace transform is we're going to be able to use the Laplace transform to avoid doing actual calculus completely. This is why engineers absolutely love the Laplace transform, because it allows you to skip all the ugly integration. All you have to do is algebra in its place, which, I don't know, maybe you feel better about integration than you do algebra, but yeah. So a couple of things down on the bottom. This page has notes about when is the Laplace transform valid. I struggle with spending any time on this, and I'm not going to. I'm just going to say the bottom of this page and the second page is really just about it works for certain types of functions that are of exponential order, because that's what we're comparing. The Laplace transform is comparing the function to. It's comparing it to an exponential. So if it's something like a tower function or something that's, that grows much faster, then you can't do it. So t cubed grows much slower than exponential. So of course it's going to behave. But e to the t squared, that's a tower function. It's not going to behave nicely. So again, the bottom of the last page and this page, in the end, I just want you to be familiar that the Laplace transform, like everything in the world in mathematics, works for a specific realm of functions. The kind of functions that you and I are going to deal with. Not the kind of functions that we haven't seen, haven't played around with up to this point. Right? So that gets us to the end of page 6, which is where I wanted to stop for tonight. From page 7 on, you're going to be taking a look at how do we actually do this and use the Laplace transform in order to solve a differential equation. And so it's going to feel, the differential equation that you'll be solving is going to look pretty easy on purpose, because I want you to feel comfortable with the idea that we know how to solve differential equations already. The Laplace transform method is just making it easier for us to do one other way for solving it. So that gets me to the end of my blurb for this evening. Remember two things before next time. I want you to finish up watching the 6.1 videos that I'm going to post as soon as we're done with class, and the 6.2 videos that I want you to finish up watching, so that next time we can take a look at the classwork, kind of dig into how does this Laplace transform stuff really work. And then the only other thing I want you to do for homework before next time is make sure I know who partners are going to be. And by the way, if you're going to let me know by email, include your partner in the email. That way they know I've been communicated with. So the only rule is it can't be the person that you've just worked with in the last pair. That's the only catch.
Chris and I are a team this time.
Nope, you got to let me know later. Okay, fine, Chris and you are a team. But just do me a favor, let me know later because I'm going to forget. But I'm too hungry. I'm too hungry. Oh, I'm too hungry. I'm going to hit stop on the recording because people don't need to see me talk about how hungry I am.